Today I will give you an introduction to that. I will show you how we calibrate electrolytic conductivity cells, and also show you the facilities we have at DFM to calibrate sensors. And I will present you with various configuration, data modeling, traceability, and also talk about uncertainty computations. And finally, I will talk about recent trends in electrolytic conductivity sensors and the challenges they give us in metrology. So electrolytic conductivity measurements are attractive, and they are being used widely in healthcare, pharmaceuticals, power generations, and many other fields, because they are very sensitive. For instance, if you add 1/4 teaspoon sodium chloride to an Olympic-sized swimming pool of ultra pure water, you will observe a 4% change in conductivity. In addition, those sensors are robust, inexpensive, reliable, and they are also easy to handle and maintain. And one attractive feature by those sensors is that electrolytic conductivity measurements give direct traceability to the SI unit system. If the sensors comprise an electrolytic conductivity cell, we can measure the size of the cell geometrically, and that gives us direct traceability. And here's a photo of some commercial electrolytic conductivity sensors. And such sensors usually comprise an electrolytic cell, as shown here in its most simple form, with 2 electrodes and an electrolyte solutions in between, and with a separation between the electrodes L here. And in this case, the conductivity can be determined as the geometric parameter, which we also call a cell constant, divided by the measured bulk resistance that we can measure between the electrodes. If we apply a voltage across the electrodes, then the positive ions will be attracted towards the negative electrodes, and the negative ions will be attracted towards the positive electrode. So that means that if you apply a direct current, then the current will stop flowing, and that's why we normally use AC current to make measurements, but except at very high conductivity levels where we can use a direct current. And the cell constant in the simple case, as shown here, if we assume that we have direct field lines and we are making measurements at low conductivity where electrode polarization is minimum, then the cell constant can be determined as the length of the cell divided by the area of the electrodes. And in this case, we can model the electrolytic conductivity cell by this simple circuit diagram comprising a resistor, which represents the bulk resistance of the electrolyte, and a capacitor representing the geometry. The product of the capacitance and the cell constants is equal to the dielectric constant of the solution in between the electrodes. But with this simple geometry, we would have fringe fields, and that means that in this case we cannot determine the cell constant as the ratio between the length of the cells and the area of the electrodes. At DFM, we had then devised a differential conductivity cell, which was originally proposed by Kenneth Pratt and co-workers from NIST. In this case, we have also parallel electrodes, and then we have an insert, which means that when it's inserted, we have a longer distance between the electrodes than when we have not this insert. And the cell constant can then be determined by the length of this insert divided by the area of the hole in this centerpiece. And this means that we would need to make 2 measurements. One measurement of the bulk resistance with the center piece, and another measurements without the centerpiece. And then the conductivity can be computed as a cell constant divided by the difference in the resistance measured with the centerpiece and without the centerpiece. And this gives us direct traceability to the SI through measurements of the cross-sectional area A and the length of this centerpiece D. At DFM, we have designed another cell which we normally use at low conductivity levels. It's a coaxial cell with an inner electrode and an outer electrode, and then guards on each side of the electrode. This means that we will have essentially no fringe fields, and the cell constant can then be computed as a logarithm of the outer diameter of the inner electrodes and the outer diameter of the outer electrodes, and then divided by 2 pi and the height of the electrode. And the conductivity is then computed as this cell constant divided by the measured bulk resistance. Now I said that we could measure the bulk resistance and then determine the conductivity, but it is more complicated than that. Normally, as I said in the beginning, we would need to make AC measurements, and we normally do that by using an LCR meter. And here we will see plots of the imaginary part of the impedance versus the real part of the impedance as measured by an LCR meter with this primary cell we devised at DFM. And here is shown 4 different conductivity levels at the level of ultra pure water at 130 microsieverns per meter, 1,500 microsieverns per meter, and 10 millisieverns per meter. And at the low ion concentrations, we can model the data using this simple RC circuit. And we see the data points here that when we are going from right to left with increasing frequency. And the bulk resistance can then be determined as a cross section between the data points and the x-axis. And with this simple model here, we can model the data with this solid curve here, and we see that we get a good fit to the data points up to about 1,500 microsieverns per meter. But at the highest concentration, we cannot model the data points by this simple circuit. As you can see, this solid curve does not fit the data points very well. Then we need a more involved model, as shown here, where we have 2 constant phase elements which are like distributed capacitors. In this case, we have then plotted the results of modeling, and we can see here that these dash curves model the data points very well, but not the solid curve. We can also model the data by plotting the real part of the impedance versus the inverse frequency, and then extrapolate a fit towards 0, where the 1 over the frequency is 0, and then obtain the bulk resistance of the electrolyte. And with this data modeling, we get similar results as with the data modeling based on the imaginary part versus the real part of the impedance. Alternatively, we can solve the Poisson-Nernst-Planck's equation and model the data. There are basically 2 main methods of calibrating electrolytic conductivity cells. One method, which is normally used at low conductivity levels, is based on a closed flow loop setup where the device under test is mounted in the same flow loop as the working cell or primary cell, where we know the cell constant. In this case, the cell constant of the device under test can then be computed as a measured bulk resistance of the DUT divided by the measured bulk resistance of the reference, and then multiplied by the cell constant by the reference, which is known. Another way, which we call method B, makes use of certified reference material. And in this case, the electrolytic conductivity cell is immersed into the reference material, and then the cell constant of the DUT can be computed as the certified value of the certified reference material multiplied by the derived bulk resistance from the measurements. We can make uncertainty computations for the two different methods, and a table is listed here which shows examples of the results. As I said before, the closed flow loops system is normally used at low conductivity levels, and for at higher conductivity levels, we normally use certified reference material to calibrate the sensors. In the case of the method A, the closed flow loop setup, the main contribution to the uncertainty is geometric measurements of the primary cell, resistance measurements by the LCR meter, and then temperature gradient. And that gives us a total standard of uncertainty less than 0.17% relative in the range from ultra pure water level, 5.5 microsieverns per meter, up to 140 millisieverns per meter. For the measurements based on CCEM in the range from 10 millisieverns per meter up to 25 sieverns per meter, the main contribution to the uncertainty is the CCEM stated standard uncertainty. But again, we get a total standard uncertainty of the order of 0.17% or less. So with the two methods covering different ranges of electrolytic conductivity measurements, we get similar standard uncertainties. So with those two systems, we are able to cover a wide range of conductivity levels from the level of ultra pure water through pure water, where we have a defined value here of 1.3 microsiemens for water for injections used in pharmaceuticals, and then dialysis around a little bit more than 1 siemens per meter, then seawater up to a point where electrolyte solution is close to its saturation points. So with potassium chloride, we can go up to like 30 siemens per meter. And with the closed flow loop system, we are able to cover a range up to about 140 millisiemens per meter. And with the open working cells, we are able to cover a range from 10 millisiemens per meter up to around 30 siemens per meter. And at DFM, we have made a comparison between the two methods. One is based on the closed flow brew system, and the other one is based on open working cells, which are also used to put in the production of certified reference materials. And those open working cells are calibrated against our differential primary cell. And we can see here in this overlapping region from 10 millisiemens to 140 millisiemens per meter, there's a good agreement between the two systems. So the diamond symbols here are from the closed flow loop system, and the circle systems here from the measurements by the open working cell, and they give good agreement, and the difference is less than the expanded uncertainty plotted by these error bars here. And we have also participated in a comparison recently with other groups, which was headed by Stefan Schweitz. And in this case, we got an agreement better than 0.3%. Commercial electrolytic conductivity sensors normally use the time domain. As I showed you before, the measurements that we make in metrology is usually based on in the frequency domain, and that can basically give a better, a lower uncertainty. But in the time domain, we are able to make faster measurements, and so this is and also the electronics is also simpler. So this is normally what is being used commercially. So what is normally made is that pulse trains of current is applied to the electrodes, and then the voltage is measured across the electrodes. And then the resistance, the bulk resistance of electrolyte is then derived as the ratio between the measured voltage to the applied current. And the electrolytic conductivity of the DUT cell can then be determined either by comparing to a primary cell or a working cell with a known cell constant, or it can be calibrated in certified reference material. But one thing we observed by these instruments is that if we make an electrical calibration where we attach standard resistors to the readout unit, and then make a wet calibration where we attach the sensor and then immerse the sensor into electrolyte solution and make calibration, we can see that sometimes the electric calibrations where the resistors simulate the conductivity, that we get low variation in the relative difference between the reference measurements and the measurements as read out by the DUT. But at the wet calibration, we can sometimes see that we at higher conductivity levels have a deviation of more than 1%. So if you use the a standard, an ASTM standard, which says that you make wet calibrations at a certain data points where it's easy, for instance at a medium conductivity level where the effect of diffusion of CO2 into the solution is minimum, and then you can make an extrapolation to the lower values of electrolytic conductivity because you have data from the electrical calibration. But if you do that, for instance, if you take a calibration point here and then assume that the instrument behaves in the same way at lower conductivity levels, then you will get an error which may be of the order of 1%. There are a number of different designs for sensors which can be used to measure electrolytic conductivity. And for the commercial sensors, normally a coaxial cylindrical configuration is used either with a 2-terminal or 4-terminal configuration. But the trend is then wireless, and this can be done in a way where you have a wireless sensor and then you have, for instance, Bluetooth communication to a mobile device, and then via a Wi-Fi link you can have data transfer to the cloud. But this can give us some challenges if we use the ASTM standard, as I told you before, where you make electrical calibrations of the readout unit and then make a calibration in a solution with the sensor and the readout unit. This type of measurements is not possible with wireless conductivity sensors because the sensor and the readout unit they are integrated in the same unit. So you cannot make this separation, and that can sometimes make it difficult to make fault detection. Is it your sensor that has problems, or is it your readout unit? So in conclusion, you can say that electrolytic conductivity sensors are attractive because they are simple, robust, and sensitive. And we can also see that there are many applications of these measurements. And one attractive feature about them is that they are direct traceable to the SI, and they cover a wide dynamic range. And this traceability can be obtained by geometric measurements of a cell constant. And recent trends are intelligent wireless sensors, and as we could see, they challenge existing standard method. So thank you for your attention.